We're asked to use the following initial rates data to determine the rate law for this reaction. We're given the balanced equation. So rate laws give us the relationship between rate and concentration of reactants for a reaction. In other words, it'll tell us how changing the concentration of one of these reactants will affect the speed of the reaction, if it affects it at all. So the rate law can be written in the form rate equals the rate constant K times the concentration of one of the reactants, in this case ammonium, raised to some power, let's call that X for now, times the concentration of the other reactant, in this example it's nitrite, raised to some power, let's call that Y for now. These exponents are known as orders, and they're determined experimentally. And so we're given experimental data, and we're going to use this data to determine the orders in respect to these reactants. So let's work on finding the order with respect to the ammonium ion. In other words, the effect that changing this concentration has on the speed or the rate of this reaction. To find the order with respect to the ammonium ion, you want to look at two experiments where the concentration of ammonium changes and the concentration of other reactants do not. So we want to compare trials 2 and 3, because during trials 2 and 3, the concentration of the other reactant remains constant. You don't want to go 1 and 3 because the concentrations of both reactants are changing, and then you won't know which one caused the change in the rate. Between trials 2 and 3, the concentration of ammonium was doubled. So how did that change the rate? Notice the rate also doubled. So we can find the order by using that information into the rate law. So by doubling the concentration of the ammonium ion, the initial rate doubled. So 2 raised to what power will give you 2? That's the question you want to ask. So 2 raised to the first power gives you 2. So this reaction is first order with respect to the ammonium ion concentration. Now we don't write ones, but I'm going to keep that just for visual purposes for now. Now let's work on finding out the exponent or the order with respect to the nitrite concentration. So again, what two trials or what two experiments do we have a change in the nitrite concentration but no change in the other reactants? So we need to compare experiments 1 and 2. Because experiments 1 and 2, the concentration of the ammonium ion is held constant. Now, between experiment 1 and 2, the concentration of the nitrite ion is doubled. So, did that affect the rate of the reaction? It did. It also doubled. So we can also say this is first order with respect to the nitrite ion concentration. Again, we don't write ones, but we'll keep it there for now. By the way, the overall reaction order is the sum of the individual orders. So this reaction is second order overall. Now let's use what we know about the rate law to find the value for the rate constant K. Before we move on, actually, let me emphasize these orders just happen to coincidentally match the coefficients of this balanced equation. 1 and 1. But that's just a coincidence. You can't use the coefficients on a balanced equation to determine the orders of the rate law. There's one exception, which we may cover later. All right, now let's solve for the rate constant K. To solve for the rate constant K, You can pick any trial and use that experimental data. I'm going to use trial 2 because it has the easiest numbers for me to calculate. But you can try any one of them and you'll get the same answer. At least on a test, all trials will give you the same answer. Now, in real life, each trial may give you slightly different answers. Nevertheless, it should be close. All right, in any case, let's use the data from trial 2. So before we do that, I'm going to rearrange this equation algebraically, save a little bit of time. So I'm solving for the rate constant K. So that's going to equal the rate over the concentration of the ammonium ion reactant raised to the power of 1, which I'm not going to write anymore, times the concentration of the nitrite ion concentration raised to the power of 1. I'm not going to write ones anymore on the exponents. So let's just plug in these numbers from experiment 2. Experiment 2, the rate is 2.70 times 10 to the negative 7. And since that's a rate, that's moles per liter second, or simply moles times second to the negative 1. I'm sorry, not moles, molar. But you could use moles per liter if you want. Now the concentration of the ammonium ion is 0.1 molar, or 0.1 moles per liter. And the concentration of the nitrite ion in experiment 2 is 0.01 molar. Or moles per liter. All right, notice one of these molars are going to cancel top and bottom. And now, because our numbers are all multiples of 10, we don't need a calculator for this. This bottom here is just going to be moving the decimal one more that way, because you're dividing by 10. When you're multiplying by 0.1, you're dividing by 10. And therefore, we can simply, to get the denominator to be 1, just move the decimal here 3 times. And so our answer is going to be K is equal to 2.70 times 10 to the negative 4. Now the units we're left with is moles to the negative 1 times second to negative 1. And there's many variations you can use. That's actually not our... I'll circle that for now. All right. Other possible common answers might look like this. Since molar is moles per liter, we can put moles per liter. Now this is reciprocated, that's why. And seconds would go on the bottom. So that's another common way you could rewrite this, both meaning the same thing. Now let's write the final rate law that includes this rate constant K. Actually, for the value for the rate constant K, it should be in 2 significant figures, because this measurement only has 2 significant figures. So we need to chop that down to 2 significant figures. So let's write our final rate law that includes the rate constant K. So it goes as rate equals 2.7 times 10 to the negative 4 molar to the negative 1 seconds to the negative 1 times the concentration of the ammonium ion raised to the power of 1, which I'm not going to write anymore, times the concentration of the nitrite ion raised to the power of 1, which again I'm not going to write. So there's our full rate law for this reaction at this temperature. Once you change temperature, the K changes. So circling back to why this is practical, or at least one reason, is now that we have this rate law, we don't need to run the experiment again just to find out how fast it's going to happen. We know by changing these concentrations what to expect the rate to be.